Hello, welcome back to this Olmo series in which we will look into the training part. So in this video and the next one, I will go into the training aspect of Olmo. So let's get started. So I'm again on the GitHub page of Olmo, and there is a section on how do you reproduce the training run. And the way to trigger it is using torch run, where you specify the number of nodes and the number of GPUs, and then you call this training script with the training configuration. So these are the two pieces that we will look at. Now, torch run gives you a distributed way of spinning up jobs. So this specifies how many processes you want per node or how many GPUs you have per node. And then there's another field that has the number of nodes that you have. So if you have multiple machines, you can pass that. So let's first look at the configuration files and how do they look like. Okay, we will look into, so let's look at the 7 billion one. So this configuration part has all these parameters that go into defining the training run and also the model specs. So if you remember from the previous videos on the model part, all these things, or rather the values of these things, were left undefined. And here is where we specify. So for example, do we want flash attention? Yes. Do you want rope or alibi or alibi, however it's pronounced? Do we want wait tying? So they've specifically went against it. What are the hidden dimensions, how many layers, and so on. So the benefit of having this kind of thing is like you can scale up. I can just go for a 100 parameter model by just defining this to be 100, and then I have another config and I can just start the run. So you can like quickly try out different things by just switching around the configs. So let's see. So this kind of defines our model. So they don't have biases. Let's see, anything else? What kind of activation they have, which we went over, and what is the initialization function. So this is all pretty standard stuff. Do we want our model to be compiled for quicker execution? Yes. What is the optimizer? And what are its parameters? What is the scheduler? What is the tokenizer? Any parameters of the tokenizer? Then how often do we want to save? What is the precision that we want to use? The FSDP things. So if you remember, the modules were wrapped and it depended on what the strategy was. So here the strategy is by block wrapping. So things will be sharded according to the Olmo blocks. And then what do we want to evaluate things on? And then the training data sets. So these are the evaluations, and then the data thing contains the training data sets, how many workers do we want, and where the data sets are. So the data sets are stored as, I believe they are tokenized and stored as NumPy arrays. And there's a ton of them. So this pretty much describes everything you need to train Olmo. So with this config, you can go and reproduce the training run. Now let's look at, and this kind of describes like how many steps you want to go. Here they've defined 2 trillion tokens as max duration. I believe max duration is the max number of steps, or some kind of proxy for number of tokens. Okay, so let's go into that training script. So if we go to scripts, and I open our training script. I just realized I wasn't zoomed in, so let's see if I can do this on the fly. All right, yeah, I think this should be good. Okay, so first of all, we set up our multi-processing thing. So we begin by importing multi-processing from Torch, and we set that up. start method. Then we also set the CUDA device where this is being executed. So because this script is called through torch run, each by default, each instance of this train.py, so train.py is called by all 8 processes, and each one gets their local rank. So if I have 8 GPUs in one machine, I get 0 to 7. If I have 8 GPUs, so I have like 2 of these machines, so then my local rank goes from 0 to 8 on machine 1 and 0 to 8 on machine 2. The global rank, on the other hand, goes from 0 to 15. Then we define, like, how do we define our distributed or initiate our torch distributed, so which was imported on top. This is, oh, I guess you can't see. So let me, this is where we define CUDA, or rather set device. This is, we initialize distributed process, and then we load in our YAML. And note, the YAML is being loaded into each of these instances of this train.py, and we call the main function, which is again below. All right, so I think that part is done. Let's look into the main method. So the main one takes the config and then sets a bunch of pulls in a bunch of values, like what is the precision, what is the batch size, and so on, optimizes states. And note, we only want to log things or display configurations when the rank is 0. If you don't have this, as I said, each process is running this script. They're communicating with each other, but each process or each GPU is running this script. And what happens is, if you don't have this, all of them will try to log information, all of them will try to print it. But we don't want like the same information being repeated like gazillion times. We only want it once. So that's why we say that only node 0, when the global rank is 0, will log. And this is what it does. What Barrier does is it will wait for all the GPUs to be in sync. So here, GPU 1 is busy printing things. The Barrier stops all the other GPUs from starting the next steps. It tells all the GPUs to wait till GPU 0 is done with its thing, and then move. Then we, so in this code, there is some weights and biases config, and again, Barrier, and then we start building our data loaders. And again, Barrier. So it's a good practice every time to set these barriers. Then we, or rather than they, instantiate the model, and the model is not instantiated on the device. If you saw the config, I didn't point it out, but the device that it should be initiated on was called Meta, and that means it's not really instantiated on your device. So despite however big model I instantiate, it's not instantiated immediately. Let's actually look into it. So this is the documentation on the meta type. So the meta type is an abstract device which denotes a tensor which records only metadata but no actual data. So we stored the specs of the tensor, but it's not really stored. So let's look at some implementations. Let's see. So it says models can be loaded onto a meta device, allowing you to load a representation of the model without actually loading the actual parameters into the memory. So what that means is the tensor shapes are loaded in. You can do the computation in terms of the shapes, not the data. So here, for example, we save a tensor, and then when we load it as meta, the shape comes back, not the data. That's the benefit of these meta things. Okay, so now we load, and of course, let's say your GPU size was limited, then you can't really load this config. You can't really load the model. So so that's why this is helpful. Like we initiate the model without actually loading in the parameters. Then we basically set the activation checkpoints, and then we look into how to set up our distributed setting. If the strategy is DDP, in that case, we initialize a DDP model. If the strategy is FSDP, then we initialize an FSD model with the wrapping policies, the sharding strategy, and so on. And then finally, we build our optimizer, we build our scheduler. Let's see where these things are defined. Okay, so I guess these are defined in the optimizer. We don't need to look at that. Let's just assume it's built. Like we can't look into all the details. Now, in this context window, they define this class trainer with the config, the model, and the distributed model, the base model and the distributed model, and the optimizers, schedulers, and all the good things in the world. We will look into what this trainer is. It basically does the heavy lifting. We will look into it in the next video. But in this context window, they define the trainer, and then basically do the training. So first thing is they try saving the model just to ensure everything is working correctly, and they try loading it again to ensure that everything is working correctly. Once that is done, we actually load in a checkpoint if there was one. So that's that. And then pretty much, obviously, if you load in a checkpoint, you kind of want to also load in your scheduler and your optimizer states. And then, if you remember, there was this compile config. We see if we want to compile our model. So that's that. And then basically we trigger training. That is pretty much it. Now, this is just a wrapper to make trainer work, and most of the heavy lifting is done within the trainer class, which is the subject of the next video. All right, I think I'll end here. Thanks for watching. See you.